Now, how do we solve systems of differential equations? Generally, there is a consistent method to solve homogeneous or non-homogeneous systems, linear systems with constant coefficients. In class, we are going to only cover homogeneous systems. So whenever there is the right-hand side, there is kind of a version of variation of parameters to do it, but we are not going to do it. So you are welcome to read about it. My purpose now is not to train you in how to solve systems of differential equations manually, because again, you can do it in Wolfram Alpha, that's very easy, but rather to explain what the solution methods of systems of differential equations. So what do they imply for qualitative behavior of systems of differential equations? So let me explain what I mean. So first, let's look at an example. So here the matrix of the coefficients is 1, 1, 4, 1. And then if you plot the direction field, so notice some funny thing, that there are two lines. So there is this line and there is this line. So that along these two lines, all the arrows from the direction field, they are parallel to this. So they just go along this line, right? In terms of the differential equation, it means that there are some solutions that just go along these lines. So the other solutions are a bit tricky. So I mean, so that there is clearly some solution somewhere here or somewhere here, but those are hard to find. But at least we know that there is a solution of the form. So here the lines are 1, 2, so which means that y is 2 times x, so that there is a solution of the form that x is some function of t and y is 2 times x of t. So that's going to be this solution. Then you can try to substitute it and figure out what x of t is. But anyway, so a little problem that what do these two vectors 1, 2 and 1, minus 2 have to do with the matrix. So this is something that you should remember from your linear algebra 2 course. I suggest that you stop the lecture and try to think about it, but later I will explain what it is. All right. So let's recap. The phase portrait shows that solutions with the initial condition above the line x equals minus 2, so above the red line, they eventually approach the blue line. And solutions with the initial condition below the red line, they also eventually approach the blue line, but on the other side. And then there are solutions that exactly follow the red line and the blue line. So the solutions that follow the red line, they approach the origin, and solutions that as t goes to infinity, and solutions that follow the blue line, they eventually go away from the origin. So they approach the origin at negative infinity. And again, from this plot, we know that there must be something like this, or maybe something like this. Which one, we don't know. So we only know that there must be a solution where the y function is twice the x function. So let us now solve the system. Right, so since we have done a lot of differential equations already, and for linear differential equations, so very often we have our exponential function, so we are going to make an educated guess, right? So we are going to assume that we are going to look for a solution in the form some fixed vector times the exponential function, all right? So here, this xi is the Greek letter xi. So notice that on the print it is a bold xi, but when I handwrite it, I think it's easier to denote the fact that it is a vector by the arrow. Right? So this xi is actually the vector with two components, xi1 and xi2. So suppose that it is a solution. So then we are going to plug it into the system. And then notice that when you plug it into the system, then in the left-hand side we have e to the rt, and in the right-hand side we also have e to the rt. So this cancels out, and I hope you recognize this equation from linear algebra 2. Right? So that is an equation from the definition of an eigenvalue. So this an eigenvector. So this equation tells us that xi is an eigenvector corresponding to the eigenvalue r. Right? So what this computation tells us is that whenever, and of course it works backwards too. So whenever xi is an eigenvector corresponding to the eigenvalue r, then x of t in this form, which is xi times e to the rt, is going to be a solution of the corresponding system of differential equations. So in our case, we have guessed eigenvectors from the plot. Right? So now I can tell you that those blue line and the red line were actually eigenvectors. Or, well, strictly speaking, they're not eigenvectors, they're eigenspaces. Right? So lines parallel to eigenvectors. So, and if we know the eigenvector, then so remember that strictly, so if you don't know eigenvectors, then the way to solve, to find eigenvalues is to write a determinant a minus r I equals 1. So this is if you don't know the eigenvectors, but sorry, 0, of course. But if you know eigenvectors, then it is much easier. So you just multiply your eigenvector by the matrix. So according to the definition of the eigenvector, what you are going to get is proportional to the eigenvector, and the coefficient of proportionality is the eigenvalue. So that's how we know that eigenvalue is 3, and here we do the same thing. So that's our xi2, whatever second eigenvector. So notice that when we do the computation, so the coefficient of proportionality is -1, so the eigenvalues, that's the second eigenvalue. All right, so now let's go back to our example. So suppose that we have not seen the picture. So if we do not know the eigenvectors, then the first step would be to find eigenvalues according to the standard procedure from the linear algebra. Then we could compute eigenvectors according to another standard procedure from linear algebra. And then you just compose it into a solution. So the first eigenvector goes here. Then its corresponding eigenvalue is 3, so it is here. The second eigenvector goes here. The corresponding eigenvalue is -1, so it goes here. And that's the answer. All right. So the definition that zeros of the right-hand side generally are called equilibrium solutions or critical points. Right. So there are different types of critical points. The list is longer than in Calculus 3, so it includes all those points that you saw in Calculus 3. So there is, well, in a way, so differential equation version of the local maximum, which is called a again, either a sink or a source, local minimum, which is the other one, and there is a saddle point, which is also called a saddle point. But here we're going to have more times, and the reason is because the matrix does not have to be symmetric, right? So remember that in calculus 3, we did it based on Hessian matrix, and the Hessian matrix, the matrix of second partial derivatives, is always symmetric. So here, the matrix of the system of differential equations does not have to be symmetric. So today we're going to do the case of real eigenvalues. Next week, complex eigenvalues. There is also a tricky case, non-diagonalizable matrices. So that, if you want, I suggest that you read the textbook, but I'm not going to cover it. It is technically, it is doable, but it is much more complicated. All right. So let's go through a couple of examples. So the first step is to find eigenvalues. So notice that here we have the luxury of working with an upper triangular matrix. So this coefficient is 0, which means that the eigenvalues are just on the diagonal, right? Eigenvectors you have to find. So here is how you can find eigenvectors. That's how I write it down. So maybe your linear algebra lecture taught you a different way to write it down. It doesn't matter. So the important thing is that you need to write these two equations. Right? So that's a system of differential equations with two unknowns, and according to the nature of eigenvectors and eigenvalues, this is going to be a redundant system. The second equation is proportional to the first one. Or, well, in this case, the second equation is going to tell us that xi2 is 0, sorry. And then if we exclude xi2, then the first equation is redundant, actually. It doesn't tell us anything. And then you can always find an eigenvector that has, I don't know, a nice integer coefficients, or maybe it has a unit length, up to you. Right, that's the other eigenvector. So, and again here the second equation is redundant. It just tells us that, 0 equals 0, whatever. And then xi2 can be anything. And if xi2 is anything, then xi1 is the same as xi2, and that's why I wrote 1, 1. Okay, and now the general solution is made out of eigenvectors and eigenvalues. So that is more or less simple. In the sense, it is not simple, but there is a very specific procedure that you can follow, and you can find eigenvalues, then eigenvectors, and then put all this information together to write down the solution of the system of differential equations. But now let me do something that may be harder. So now you have to make an effort to understand it, right? So some qualitative observations. So notice that first, as t goes to infinity, since both eigenvalues are negative, right? So if t approaches infinity, this approaches 0, this approaches 0. So all solutions approach the critical point 0, 0. So on the phase portrait, it means that all direction field vectors, they kind of point towards 0, and all the solutions are going to flow in towards 0. So another thing, so notice that as t goes to infinity, so we have these terms, so both of them approach 0. But if, say, the first of them is going to be, let me just, for the sake of presentation, write that this is going to be some, I don't know, alpha. This is going to be a very small number. But the other one, if this is e to the power minus 0.5, then in order to get e to the power minus 1.5, you need to cube it, right? So this is, if the first of them is alpha, then the second is alpha cubed. And now imagine that if t is a large number, then e to the minus something t is going to be a small number. So alpha is going to be a very small number, but alpha cube is going to be so much smaller than alpha, then it is just negligible. So, which means that when t approaches infinity, we can just forget about this term. It is so much smaller than the first term that we can ignore it. So the first term dominates, which means that, and the first term tells us that we have the vector 1, 0 times some scalar, e to the minus 0.5 t and times c1, right? So it is proportional to the vector 1, 0. So it means, geometrically, it means that when solutions come close to the origin, then they will do so not just chaotically, but rather they will approach the origin along the vector 1, 0. So they are going to be parallel to the line y equals 0 in a way. And then we can repeat the whole thing, right? So imagine that if t goes to minus infinity, right? So now, still, if this is alpha, then this is alpha cube. But now, if t goes to minus infinity, then minus something t is going to be a positive number, and both terms approach infinity. But among them, both alpha and alpha cube are very large numbers. But of course, alpha cube is going to be so much larger than alpha, then you can just forget about the first one. And then you can just look at the second one, and now it is parallel to the vector 1, 1. So it means that solutions, when they are far from the origin, they are going to be parallel to the line y equals x. Right? And here is the actual phase portrait. So notice that, again, we have 1, 0. 1, 0 is this vector. So let me write it here. So that's the vector 1, 0. Yeah, and notice that in the neighborhood of the origin, all solutions, they do approach the origin, but when they come close to the origin, they are tangent to the vector 1, 0. And that's because the vector 1, 0 is here. It corresponds to the eigenvalue. So both eigenvalues are negative, but close to the origin, everything is dominated by the vector corresponding to an eigenvalue that is smaller in magnitude. But now, far from the origin, the other eigenvector is 1, 1. So let me maybe write. So that's 1, 1. And indeed, you see that far from the origin, so around here, everything becomes parallel to the vector 1, 1. And this is because this is the eigenvector corresponding to the eigenvalue that is bigger in magnitude. Okay. So now let's go through the general recipe. And so if you want to solve a homogeneous linear system of n differential equations with constant coefficients, so you need to take the matrix of coefficients, then you need to find eigenvalues of that matrix. So if all of them are real, then we know how to do. So if some of them are complex, then next week. Then you need to find eigenvectors. So now if the matrix is diagonalizable, it means that there are n linearly independent eigenvectors, and then we are done. So we know how to do it. If the number of linearly independent eigenvectors is fewer than n, it means that the matrix is not diagonalizable, and we are stuck. And I'm not going to actually teach you how to do it. It is doable, but it is more complicated, and you can read about this case in the textbook. And then the general solution of the system of differential equations is going to be given by this formula. So it is, we put eigenvalues and eigenvectors together. So